left off. So as she mentioned, in our first WIN project, we studied these intersection numbers and the conjectural formula of Brunel-Yang, and we saw that it didn't really match up. And while we had some guesses for some things, there were still some fractional powers. Then this 23 we couldn't understand. So when I went to intern, we really wanted to look at sort of if we could come up with a formula that would work in more general cases. So that was our goal, and luckily we obtained our goal, but this is much later. So we're still writing up this paper, and my internship was a long time ago. Okay, so what is the intersection that we want? We want to look in the ambient space of abelian surfaces. We want to count the number of abelian surfaces that split both as a product of elliptic curves and have this embedding. And that can only happen over a finite field. We saw that can't happen in characteristic 0. So this intersection number that I write down, you should think of it as counting these objects that land both in this locus and in this locus over FL bar. Okay, so we have some assumptions. I can't get away with nothing. So we assume that OK is freely generated over OF. L is not 2, and L does not divide d minus a square over 4 for any positive integer of this form. Okay, so then there is an explicitly computable formula for G1 Cm of k. So for this intersection at L. So counting the number of abelian surfaces that have both of these properties over FL bar. So I will build up to writing the entire formula down over the talk. So let me just put it up here. So if k is nice enough, so in simple cases, then this G1 of Cm of k, the L part. So usually when you write these intersection numbers, you write them sum over all primes L, and then you weight them by log of L just to say which is coming from what. So this is really just the number counting what I said. So we have 1/2. You sum over delta, which is of the form d minus a square over 4. Then you have a constant, either 1/2 or 1. So this is and we sum over these values n. So that you get some positive integer divisible by L, and there's some congruence condition. And then what do you get? You count the number of ideals so Brunel-Yang counted the number of ideals in this real quadratic field. So we count the number of ideals in a complex imaginary quadratic field. You'll call it n. And then you have some valuation. Okay, so that's what you get in a very nice case. So it looks very Brunel-Yang-like. I don't know if you remember the whole formula, but you had to sum over these deltas of exactly the same form. You just sum over these integers L. It was a slightly different condition, but it looked the same. Then there was some valuation and some number of ideals of a given norm, but both of these were taking place in a real quadratic number field. Instead of here, we're just taking valuation and in the integers. Okay, so this formula It looks kind of scary, but I promise it's not actually that scary. So one thing that's nice is you just concretely study these objects with the embedding problem like Kristen talked about, and you very naturally come up with these objects. So I will give a sketch of the main idea of the proof, and hopefully that will make this look not so scary. But some important things that you should notice is, one, that it looks similar to the Brunei-Yang. I mean, the objects appearing are the same, the summands are the same. That looks similar. And also that this is like something that you can very easily compute on a computer. So yeah, you have these ugly summations and things to check, but that's something that can very easily be put into a computer. And since the goal is to use this to compute curves for cryptography anyway, I mean, the whole purpose is to put it on a computer. So we're not losing anything, even though it looks kind of ugly. Okay, so let's unwind some of these definitions. Okay, so we want to compute this arithmetic intersection number. So what is an intersection number? Well, classically, you're supposed to think of these varieties on some space, and you're counting the points that appear in the intersection. And that's what we're doing, except now we're just doing it over FL bar instead of over Q. So we sum over points in the intersection of these two subvarieties over FL bar. But then you count them with multiplicity, right? So then we weight each point by... So each point corresponds to an abelian surface in this embedding, so there are some automorphisms. So we divide by the number of automorphisms our point has, and then we have the multiplicity. So this is the length of P. So if you imagine two things intersecting, at this point, if they come together in their tangent, when you look locally at this space, there's some little tangent vector there. And that's what this length is measuring. So that's just measuring the multiplicity of the point. So when we wrote our algorithm before to count the number of embeddings, we explicitly described every point P, but we were unable to compute this quantity. Okay, so that we have to make sure that whatever we're going to do, it's going to allow us to compute this quantity. That's what was missing before. Okay, so let's unravel this a little bit more. So we want to look at the points. Well, what does this point correspond to? So the point is an abelian surface, but it's lying on the Humbert surface. So that means we're just looking at a product of elliptic curves over FL bar. And it also lies in the CM locus. So that means we have an embedding. Okay, so this is exactly what Kristen mentioned in her talk. So you get so a point is exactly a pair of elliptic curves plus this map. Okay, that's all a point in this locus is. So we want to count the number of times this appears. So if we assume OK is freely generated over OF, that means that OK equals some OF adjoint eta. So then this map is determined just by two elements, lambda 1 and lambda 2. And I'll just write the endomorphism ring of the product, where you think of lambda 1 as the image of a generator of the real quadratic maximal order, and you think of lambda 2 as the image of this extra generator. Okay, so all we have to do is sum where the generators go. So we've reduced this map to just looking at those two elements. Okay, so then let me just assume, so we have some fixed eta. So it comes with the information of what its trace is, its relative trace, and its relative norm. So we just find this generator and then calculate those numbers. So if you expand what it means for lambda 1 to be the image of this element and lambda 2 to be the image of that element, that gives you some relations. You also know that OK is commutative, so that gives you some other relations. So you write it out explicitly, and you get that lambda 1 has to look like this, lambda 2 has to look like this. Where a is an integer, the degree of b is of the form d minus 2a squared over 4, which we'll call delta. You have some commuting relations, plus 5 other equations relating the degree and trace of b, x, y, and z. Okay, so you get these very, very explicit equations for what an embedding is given. And you already see, so this delta is going to be the same delta. Okay, so that delta is just telling us that degree. So, but I made a choice here when I wrote it in this matrix form. I mean, I picked which elliptic curve was E1. So if I switch E1 or E2, then that will switch the roles of A and D minus A and X and Z. And so by possibly switching E1 and E2, we may assume that A is less than or equal to D over 2. Oh, this is supposed to be D over 4. It's not, so it doesn't matter so much. Okay, so that's fine. That will uniquely determine it, except when A is exactly D over 2, I'm going to double count. So that's all that little constant is. It's just taking away this double counting when you're exactly on the boundary. Okay, so A is thrown out. That's completely determined by delta. And now B is something of that norm. Okay, so from now on, we'll think of fixing delta, and we want to count the number of x, y, b, z, where these are isogenies and these are endomorphism rings that satisfy all of these properties. Okay, but now let's go back to what I said about the length. So we really want to calculate the length, and that's so when you're thinking of this multiplicity, what it means in this moduli space interpretation, it means like how much these elements deform towards characteristic 0. So you know this embedding can't be lifted all the way to characteristic 0. But sometimes it can be lifted over some quotient of the Witt vector. So it can be lifted to some epsilon thickening of FP, like FP epsilon mod epsilon squared or mod epsilon cubed. That's what we want to calculate. Say that again?
Does it matter from your perspective how far you can lift it?
Well, how far you can lift it is exactly what this length is measuring. So if we want a formula for that, so it doesn't matter in like, I mean, we need to know it to compute, but it's not telling us like something interesting about the embedding. Well, except for how much it lifts. Yeah, so we really want to be able to keep track of this. And when you have two elliptic curves, so you want to deform both of them towards characteristic 0, and how do you do it? Do you do it independently, or do you do it both at the same time, or is there some relation? So controlling two elliptic curves is much harder than one. So we'd really like to reduce our picture to just looking at one elliptic curve and deforming that. And that's also been studied a lot more in the literature. So what we're going to do is we're going to take this x, y, b, z, and we're just going to think of two endomorphisms. So now this is all in the endomorphism ring of one elliptic curve. So I take this tuple. So I just forget about z. I mean, z is sort of related, sort of determined by the other ones. If I could divide by b, then I could definitely determine z in terms of the other ones. And so then I just take y and then b dual back, and that will give me an endomorphism of the elliptic curve. Okay. Okay, so what do you do when you want to count something in math and you don't know how to count the whole space? I mean, we do this all the time. You make a fibration and you count the base and you count the fibers and then you count the whole space. So that's exactly what we're going to do here. So we finish in 3 steps. So one is counting the base. So we count these xu. So I'll just put the elliptic curve in there. Satisfying. So you take all of these conditions and then you see what they give you for the x and yb dual. So you'll get some extra conditions. And you want to count these with multiplicity. So you count the length. And then 2 is we count the size of the fiber. So for fix an xue, and then count the number of x, y, b, z, e prime, such that yb dual equals u, and they all lie in the correct space, and all of those other properties still hold. And then the last one, so that just gives you the count, but then you need to relate the multiplicity. So relate the multiplicity of this 4-tuple x, y, b, z with the multiplicity of just the endomorphisms. Okay, so I will try to give a sketch of each of these. Okay, so let's look at step 1. So what are the conditions? So these conditions that I didn't write out, what they give you in x and u is that trace of x, trace of u are all determined by delta. And then norm of x, the norm of u, and trace of xu dual are all fixed by an integer n. And this integer n is the integer n that shows up in the summation. So that satisfies, it has to satisfy these properties, and then it gives rise to a norm of x, norm of u, and trace of xu dual. Okay, so let me make a little bit of a side remark about how we're going to count this. Okay, so Kristen in her talk alluded to this paper of Grossagier. So it's called On Singular Moduli. And then there's some work by a student of Gross, David Dorman, that builds on it. So what do they study? They study D1 and D2 are negative, square-free, relatively prime integers congruent to 1 mod 4. Okay, so you can think of these as discriminants of an imaginary quadratic field. In fact, that's exactly how you want to think of them. And they studied this quantity, J D1, D2, which is a product. So you take elements in the upper half plane that have discriminant equal to the discriminant you want, and you only take classes, so mod SL2Z. And then you take the difference of the J function. And then there's just some power up here. That's not important. Okay, so what is this? Well, this is looking at a product of J function, product of difference of J functions, and Grossagier and Dorman studied the valuation of this quantity for this is a prime in O of Q adjoint square root D1. Okay, so what is this telling you when L divides this quantity? It means, well, you have an elliptic curve over C with complex, well, an elliptic curve with complex multiplication by tau 1, and then an elliptic curve with complex multiplication by tau 2, and they have the same J invariant, so that means they're isomorphic. You're counting elliptic curves with complex multiplication by 2 different orders. Okay, so that's exactly what they're counting here. So if you look here, if norm of x is fixed and norm of u is fixed, then the discriminant of x and u is fixed. So here, we're counting elliptic curves that have complex multiplication by the discriminant of x and by the discriminant of u. So this is exactly the same problem, but in this case, we have no control over the discriminants. So here they have this very strong condition that they're square-free, relatively prime integers. Here we can have something that's really not a fundamental discriminant with some huge conductor. They may have huge factors in common. So we don't have control over this. So to count this, what we do is we generalize their work, Grossagier and Dorman, to any D1 and D2 as long as one of these is fundamental at L. One of D1, D2 is fundamental at L. So that's the only information that we can get out of our setup, that we get discriminants, but L doesn't divide the conductor of both of them. It just divides the conductor of one of them. So that's the only condition we have at our disposal, and so we generalize Grossagier and Dorman to that case. And I should say the machinery that Grossagier and Dorman use and that we also have to use, it really completely falls apart when you want to look at the L valuation, but L divides both of the conductors. So you can kind of imagine that that causes a problem. And it's really a very, I mean, all of the literature in this field makes that assumption. So that's a very strong condition. So it's lucky we could at least eke that condition out of our setup. Otherwise, we'd be dead in the water. Okay, let me just point out another interesting corollary to this, because it explains the 23 condition that Kristen mentioned. So, okay, if you have if you embed a quadratic imaginary order, so let O be a quadratic imaginary order, and it embeds into the endomorphism ring. So then you can also look at the intersection of O you can look at the intersection of the fraction field of O. So you can take this embedding and you can tensor with Q on both sides, and you can ask, okay, well, when you look at the sublattice inside of here, what's happening? Do you get the same sublattice on both sides? And if you have a maximal order, then of course you're going to get everything, because you can't, this is not exactly what I want to say. Okay. Let's look at this. Let's look at Q adjoins square root G intersected with the endomorphisms. So this certainly contains your order O. And if O is maximal, then it has to be the entire thing. But if your discriminant is not maximal, then this can actually get bigger. So our count is not just by embeddings, but what are called optimal embeddings. So you sum over orders, these orders, that contain O of G, but are smaller than the maximal order, and those are giving you different counts. And those extra 2 embeddings we got for 23, for example. So there was this Brunier-Yang example where they computed 23 squared, and when we counted the number of embeddings, we got 23 to the 4th. So Brunier-Yang was missing an embedding. This is exactly what happens. So in that case, you have to sum over 2 different possible optimal embeddings. So this intersection has 2 possibilities. And that didn't show up in any of the other examples we considered. So we think somehow that assumption is showing up in their proof, but it's not it's not so clear. Okay, so let me just quickly mention some things about 2 and 3. And then I'll mention our project in more detail. Okay, so step 2. Okay, so if there exists an element in the fiber, so if the fiber is non-empty, then there is an ideal that you can get. So what is it? Well, you take, so we have an E prime here. You take all isogenies from E to E prime, and then you compose with B dual. So this gives you an ideal in the endomorphism ring of E. This is the maximal order. This gives you a left ideal. So such that some nice things hold. So this statement that I'm going to write down comes from Düring's theory. So you get that the norm of the ideal is exactly equal to the norm of this isogeny. So you get that it's delta. Well, what is U? U is Y B dual, so that shows up in here. And delta is B B dual, so that also shows up in your ideal. And then, well, I erase the Z. So how does the Z come in? Well, Z satisfied this BZ equals XB plus D minus 2A Y. Yeah. So you can sort of divide by B in the fraction field of the endomorphism ring. So if you do that, then you get this So this is playing the role of Z, but you have to think of what it means. And for it to be an endomorphism ring of this other elliptic curve means that it's in the right order of this ideal. So, I mean, there's a lot of heavy lifting going on here by Düring's theory, but it gives you this very nice concrete description of when there's something in the fiber. So we just want to count this ideal. So we basically study in depth the possible ideals in M2 of ZP. Okay, so what is this endomorphism ring? It's an order in a quaternion algebra, but when you tensor with ZP for P not equal to L, it just becomes 2 by 2 matrices over ZP. So this very explicit study of how many Vigneras has a description of all the possible ideals, and then you translate all of these conditions. And it reduces to like studying solutions to a quadratic equation mod powers of P. So you have this extra factor we have to add here. Well, this frac I. Okay, so first you sum over these F. So those are the summing over the possible orders. Then you add in this ideal. We have to add tildes here. Okay, I'm not going to describe that part. It's the same setup, but it just gets a little bit more complicated. And then for step 3, so we get that if L does not divide delta, so we're just looking at the multiplicity mod L, right? So delta is the degree. So you should think if L doesn't divide delta, then that means when you're doing deformations, B is kind of invertible. I mean, you don't really get to invert it, but you get to pretend like you can invert it. So that means if we can deform X and U and pull them along, then we can divide out by B. We can pull along Y for the ride. We can pull along Z for the ride. And so all of the multiplicities stay the same. So if L does not divide delta, then the multiplicity of X and U is exactly equal to So this is this length that I mentioned at the beginning. So that's why we have this condition about L. So if L does divide delta, then what we get is an upper bound. So I won't write it down. But if L does divide delta, then this multiplicity is bounded above by twice the multiplicity of x and u. So we don't get an exact formula in that case, but we get a bound, and it's pretty good. Okay, so then in my last few minutes, let me mention what our project is for this one. Okay, so let's write our formula down. So Brunei-Yang, under their assumptions, so under some assumptions. So I'm going to write it a little bit differently than Kristen to get something which looks very similar. And then you sum over n such that n plus delta square root d tilde over 2d is in this inverse discriminant. And then you get and then we sum over these frac L's in OF tilde. So we also had a lot of discussion with the frac L's. So you take t plus 1, and you take the number of ideals in this extension. And then there's the inertial degree of this L. Okay, and let me sum over the n. Well, maybe I can just compare on the two boards. Okay, so this is the Brunei-Yang formula. And in nice cases, so ignore the yellow, this is our formula. Okay, so it looks pretty similar. We have the 1/2, we have this delta, then we have this constant, but Yang assumes that d is prime. So you can never have delta be d over 4 in his case. So this is just 1. Then you have this n. So the conditions look kind of different, but this condition that we consider is basically the norm of this element that they look at. Okay, so then they have to sum over these ideals L. We're working in Z, so we don't have any extra ideals. And then you take this valuation, and again, this norm of the t is exactly, basically the n that we consider here. Oh, sorry, I put 1/2 twice. This half was supposed to be there. So you get the valuation plus 1, valuation plus 1, and then number of ideals of a certain norm. Okay, so the proofs of Brunei-Yang formula and of our formula are completely different. But what you get out looks very similar. And you would think just without using the proof, just using number theory methods, you would be able to directly compare this formula with this formula. And then maybe then you would be able to get stronger conditions about when Brunei-Yang actually works. So we know it works for d and d tilde that are 1 mod 4 and prime. But we saw some examples where it works in more generality. So our project is to explore the connection. I mean, this can't just be a coincidence. So we know that the sums are the same, but we'd like to know that each individual element is matching up, corresponding to what you think it should be. And we've already made a lot of progress. So my group will tell you about that on Friday. Okay. Everyone wants to go to free afternoon?
Yeah.